reader in principal component, what's your title?
Theoretical computer science.
The reader in theoretical computer science is going to do on robust principal component.
Thank you. Actually, I'm not really ready for the talk, although it's really a time for me to give a talk. But thanks to Chris, I'm standing here to share with you my new investigation. So this topic, robust principal component analysis, is pretty new to me, only 10 months old for me, although it is about 6 years old to a reasonable group. So I will organize this seminar along my own footprint on the research on this robust principal component analysis. I will start with classification and clustering, which is a typical pattern recognition problem. I used PCA, well established PCA, to the classification. And then there is a big problem with PCA, which is the sensitivity to noise. That's why in 2009, some researcher, especially in Stanford University, proposed robust PCA. Robust means robust to noise. But if this PCA is just robust to noise, it can only be applied to denoising. Okay? To further expand the application, so there's still a lot of work to do to widen the application areas for PCA. So there's another issue with PCA. This the robustness is actually a two-sided one coin. Right? I will explain again in the talk. I have done very initial experiment on video surveillance, but I'm still, to be honest, starting on some theoretical proof if I want to bring some contribution to RPCA. This is an illustration of classification versus clustering. As we know, in classification, the data are labeled. So we know, in the training data, we know which class, which data belongs to. In clustering, given data, we don't know which is which. Okay? So we need to use a systematic method to group the data into their own classes. Typically, we, for example, in some applications, we can start with any number of clusters. But typically, we know the number of clusters. So we start with some random positions. So the cluster center can be automatically converted to the final answers. So classification, so we know in classification the classes of training data are known, but in clustering the classes of the training data are unknown. So classification is also called supervised learning or learning with teacher. Clustering is also called unsupervised learning or learning without teacher. Like what I said, I follow my own footprint, so you know why I am investigation this robust PCA. Here is an example for classification. I think there's some Chinese people know. Do you know what it means?
No.
Okay.
Hold it. What do you guys?
What does it look like? What does it look like?
It looks like a man.
A man? What's it? It's wood.
Wood.
Part of a tree.
Tree.
Right?
Because trees have really big, wide roots.
There are many trees, okay?
And they're all the same symbol?
Yeah.
Including the one that's got sort of four in it?
The same character, okay? That's the point, okay? Different people have different writing style. Even from the same person, they write the same character.
But are they the same character? This last one looks like a different one. I mean,
Okay.
I'm not sure it is, so I can see. I mean, if you ask me, then probably.
That's a good point. Okay, that's why. Okay, I will go with the problem with PCA. Okay, maybe some people can also maybe in the training data you may also claim some wrong sample. It happened, right? And also for some, there's another character. Okay, there's a dot here. Some people just write like this, the same. Okay, for them. Okay, especially in handwriting.
And what does that mean, the other character?
Our character means
Water.
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 Water can also look at the same. So, how to apply principal component analysis? This is the formula. Actually, PCA itself is quite easy. Actually, in MATLAB, there is a function called eigen. You just call eigen, then PCA is done. Okay? But the point is how to use it, right? How to organize or classify these characters. So we treat every single one is a variant of some mean character, mean pattern, okay, or average pattern.
Now, may I answer? I've done principal component analysis before, and I kind of understand what that formula means, but I don't really know what it means.
Okay.
Can you tell me that PCA is this formula? Could you just unpack
This
that?
formula.
Yeah.
Okay, this is the training data.
So that's a big old matrix.
Yes.
Okay.
All matrix. Okay.
Okay.
This is the eigen vector. Okay. This is the
eigenvector or eigenmatrix. So it's just
eigen matrix. Yes. But
for instance, 0 and 1.
the components, each component or each dimension corresponds to one vector.
Yeah.
So we call sometimes.
Okay, I get it. So it's 0, 0, 0 in the middle of the matrix. What do you call it? The
Diagonal.
diagonal of the matrix that's the diagonal of the matrix.
Yeah.
Yep. And then you invert it the other way. And what's the sigma? Is it sum or is it something else?
This one.
Yeah.
Covariance matrix. Only this one is unknown. Okay. By the principal component, this one is known. Given the data, this is ready. All right.
So the entry of the sigma is the eigenvalues of D and D.
This is eigenvalues. I will talk about eigenvalues later. Okay. Eigenvalues correspond. Each eigenvector has an eigenvalue. Eigenvalue indicate how important this particular eigenvector is.
Yeah,
Yes.
basically, so how do you form this sigma? So for me, sigma is just is a connection of eigenvalues.
Oh, sorry. Yes. This eigenvalue. Sorry. This is the covariance matrix. Sorry. This is correct. Sorry. You're right. Sorry. This is the eigen. Yes. Eigenvalues. Yes. Eigenvalues. Correct. Eigenvalues for each eigenvectors. All right. Okay. Sorry. This is the covariance matrix.
Actually, this should. I mean, this is so. I mean, the sigma should be the singular value of D.
No.
I mean, each entry of sigma, the diagnosed entry should be the singular value of D. So it should be the eigenvalue of D times D transpose.
Yes. So you may have, because actually, if you don't ask me, I never care about this formula.
So what you do is you get an input matrix D, right? And you can easily derive TT from that. So no problem. And then there's some calculation which gives you U sigma and U.
Yes, this is what we call this function an eigenvalue that we can get U and a sigma.
Yeah, this is called spectrum decomposition.
Right, I've done it before. I just wanted to change. I just wanted to make sure I had it right. Cool.
See, I say that I'm not very prepared for the talk. Okay?
No, it's all right.
I beg your understanding in advance if I cannot answer all of the questions.
But D is encoding the character somehow, right?
I use the training data. Okay.
All the
Those are, each one of those is a...
Yeah.
So, So the dimension of D is the number of instances of training data? Or?
Yes, yes,
Yeah.
yes.
One dimension is, the other dimension is the number of,
One,
number of inputs for
One
each
row
training.
is
Yes,
the future.
one capital.
Future. But what is, I mean, so how do you get this U, D, psi, gamma from?
Okay. So this one is the mean vector. So we,
Cool.
you may have heard eigenphase, right? Eigenphase. So suppose we have a mean phase image, okay, across the world, okay. How many?
7 billion.
Okay, 7 billion or whatever. 7 billion, okay. We put all the phase together, the image, okay, divided by the 7 billion. So we have got a mean phase, okay. So each of us is a variable of this mean image. That's why it's mean. All right. Okay. This is the mean vector for all the characters. Okay. So through PCA, we get this eigenvectors. All right. So now it's very easy now. So as we treat every single data, input data, okay, as a variable to this mean vector. So now we can just change. Not working. Okay. We can just change parameter. This one we can change. We can change actively. Okay. We can change character. Then we can get an example, a pattern, a character. All right. And this one, for example, we have just seen 1 to 16 characters. But with this one, this is a real number. Actually, we can generate millions of thousands of characters. So which is supposed to cover all the characters, all the possible samples. So we can generate samples actively. Okay. So this is the way how to use PCA.
Can I try that again? So the U, the eigenvector, represents the ideal, the prototypical wood.
The
prototypical character.
Yeah.
The prototypical character, right?
Yeah.
And then you multiply that by a beta.
Not principal character, the principal dimension. Some. Yeah.
The first component.
The first component. Okay, I will explain what component means.
Okay. So now let's talk about the input. Input is D. So
Yes.
from this D, you can get this U. Then how do you get this psi? Psi is just the average of D.
Just the summation of all the vectors divided by the total number of characters.
Okay, so you can compute this psi.
Yes. Yeah.
Then, I mean, so what do you want? You want to compute the left-hand side?
It's a metric of distance from psi, is it?
Yeah, but okay, so you have this B, so B is some random number generator, or?
We can understand that the brute force, we can just randomly, okay? In the classification as runtime, of course, we can use algorithm. For example, speed ascent algorithm, okay? To, now given, okay, if you write a character, okay? Okay, given the character. So I use this speed with a range, okay? From, say, minus square root of speed, square of this eigenvalue. So if the valid character must be within the range of this B, alright? For example, say from -1 to 1, okay? If this one within this range, I can generate one base match to the given character. So we can conclude this one belongs to this class. The given character belongs to this class. Get it? Right?
And you do a different matrix for a different character.
Yes. Yes. Now, so let's take a further view on this PCA. Actually, PCA was proposed in 1960 something by a mathematician. There's another name is I don't remember the full name. It's called KL transform. It's two scientists' name. KL is a orthogonal transform. Okay. So we can convert actually data into some principal dimensions. For example, this one, the given data is in 2 matrices. Maybe we can just use 1 dimension to distinguish this one from others. So back to we can go back to the first example. Look here, for example, this is a two-dimensional space. Actually, we may just need one dimension to distinguish them. All right. So let's write this point for dimension induction PCA for this classification as well. So, given this character, maybe if we use some landmark point, for example, for 100 points, the original dimension space is 100 dimension. But actually, we just need only a few of them. We could just use only a few of them to distinguish all the characters. For this principal component analysis, so each component means one dimension. Okay. We don't have to interpret. Okay. But this one for just now the characters, actually we can interpret. Okay. For example, the first component dimension means the scaling. Okay. This one means translation. This one means rotation. So we only use these three dimensions can capture all the properties of all the variation within the characters. Right? So this is the properties of PCA. When PCA is applied to class, just for example, we can project data to this. This is a subspace view, okay, to this space. Actually, we use maybe this dimension, this one, okay, to distinguish all the data. This is a simplest illustration of PCA for clustering. For example, given two-dimensional data, so how can we project them to one, so to cluster? Okay, so we treat the data spread along a line with some bias, with some error, okay, with some distance. So the PCA is actually to minimize the sum of squares distance of all the data to this line, to this one dimensional one.
Yeah, but what's the difference between this and the regression?
PCA can be used for regression. Can be used
This
for
is exactly the regression, isn't it?
yeah. Yes, PCA can be used for classification, clustering, and regression. Okay, all right. Okay, PCA is a technique. You apply PCA, you can reduce dimensions. Then you can still use you can use it for regression. Right?
So, as I can understand it, so with PCA, you get the first principal component analysis, which is the best line. You do the independent component analysis, which is related, and you find the next best one. So you start to break your data down into more and more dimensions that account for data better. With principal component analysis, you take the first principal component out and then do the second principal component.
Yes.
So it's regression, big matrix techniques, you can do lots of different things with it.
Yeah, even for example, regression. So the PCA, after PCA, the dimension is reduced. So it's easier for you to do regression. Right?
Also, PCA provides more transparency because for each principal component, you can tell exactly how much each dimension contributes to it, right? This regression.
Yes. However, just now we mentioned that there may be there are lots of reasons. Okay, for example, maybe there's a wrong collection. Another reason maybe there is some pattern, some samples really belongs to this class, right? Okay, this one is easier. For example, there's a wrong collection. Even for the same person, they may the image may do different from time to time. I believe you heard some news about Hollywood actors, okay? Like on stage, look very pretty, alright? Maybe at night, they look very ugly, alright? So a bigger variation, alright? So this PCA cannot deal with it, okay? Right? So you can only allow some grossly corruption, alright? Maybe along some Gaussian distribution noise, okay? So for arbitrary corruption, PCA cannot do with it, right? So that's why we need another technique which is robust to noise. So actually this robust, this is about an outlier, or actually PCA is still a linear analysis, right? You can only provide a linear solution. For this noise, actually outlier, that means it cannot be classified linearly, or this is a nonlinear separation problem. Okay. So to deal with this nonlinear separation problem, there are some techniques. For example, this one is kernel PCA. We map or we convert the original input space to a high-dimensional nonlinear space. In this high nonlinear space, we find linear solution. This linear solution is actually corresponds to, if you back to original, this linear solution in the nonlinear space is equivalent to a nonlinear function in the original space. But this is the point of kernel PCA. I published this figure 2003 in Paris. That's why I put it there. Okay, all right. So this I draw to illustrate how
Kernel trick, not the kernel PCA.
Kernel PCA works. And another also typical solution is probabilistic framework. It's very straightforward. So for nonlinear separability, either you map this one to a nonlinear space, right? Anyway, to make it nonlinear. Another way is to use probability, right? All right. If you can find this the IDF, you can also provide a solution. So now there's another method. If we can model the noise, or we can still deal with this noise. That's why I'm investigating this robust PCA. For any problem, we have data, right? This can be anything, okay? Use, for example, neural network, machine learning, any method. Okay? This is generated model. To get to the solution, we need to view the data, something like this. So this solution is the data times some weight, something, with some bias. We call error. Error doesn't mean really error, okay? It means some bias, okay? So we can get the solution, correct? Now, for this input data, we can also build this, for example, the data. If you use a classification, regression, or whatever, okay, it must follow this model, right? Okay, it must follow for anything, for any control, or anything in the world, it must follow this model. Okay? Now, for the input data, it also follows this model. Right? So we try to view this data, also some clean data, right? With some bias error, right? So that's why we can. So we try to view those noise here, okay? Try to pick up noise from the clean data, okay? This is a robust PCA view, okay?
Sorry, what does this A?
Now we don't have A is what we can find out. Okay, we use the optimization technique to find out A. Okay.
What does A stand for?
A stands for clean. For example, if D, this is given the data here. Okay. A maybe the real image, right? E is those noise. Okay, we understand this at the moment. Okay.
So if you could mystically pull out all the bad examples. That's
Yeah. So the PCA will pick up the real image, okay, or separate the real data from the corruption, from the noise. Okay, we understand this at the moment. Okay, but later on we can expand this this view to other application. Okay, the other application, the error doesn't mean really noise. Okay? We know in some application we don't really have any noise. Alright, okay. Get it? So this is robust PCA, we treat a data combination of two components. One is called, okay, in that terminology, it's called low rank matrix. This one is sparse area. Because the data, in every application, our dimensions of interest, that's why we need to use PCA, principal component. Our dimension of interest is just only few dimensions. Okay. So for example, given the image is for a gray label image, it spans from 0 to 156, 100 times 100 matrix. This is a huge dimensional space. Actually, the data only span in maybe only 4 or 5 dimensions. Okay, right? So all the data in the mathematical terminology, data only span in a low rank space. Okay, or in some low dimensional subspace. And this area, because the robust PCA want to cover any arbitrary noise. Okay, so we assume the noise can be sparse, any errors. Okay, in any magnitude. Actually, in the proof, so we only care about the sign of the data. We don't care about how big an error is. Right? So it can be approximation. Now, I say, given that training data T, we view them as two matrices. One is called low rank matrix, one is called sparse area. Okay? So these the training data, we need to find out A and E, right? For denoise problem, so if you can separate this one, so we can pick up clean data, right? So we can denoise the A, E. So we need to find out both A and E.
But I mean, so you must have some constraints. For example, we can put A to be 0, then the rank is 0, so this must be no rank. And E just D does not make sense.
Yeah. So we need to optimize both. We optimize this A to the lowest rank, okay, make the rank as low as possible. And in the meantime, we need to optimize this sparsity area using L1 non-minimization. Okay, with these two constraints, so we can get both A and E.
Sorry, what is the rank? What do you mean by?
Okay, I will explain rank later in the last slide.
So how do you measure the sparsity of E? Because you said the first one optimize.
Sparsity, for example, for L1, okay, so we use, for example, the E, we just treat it, for example, in the,
so you use L1 norm to measure sparsity?
yes.
Okay.
To make it as small as possible, that means make it as sparse as possible, right? Okay? Alright? So this is the minimize, okay? You know, this nuclear norm plus this L1 norm subject to this data.
So L1 is just the sum of the absolute value. So if this matrix is not sparse, because like every entry is not 0, but still it could be the case that L1 is very small, because every entry is very small. And on the other hand, it could be the case that this matrix is sparse. So there is only one entry, the other ones are just 0, but that one is very large. Then L1 is still quite large.
We have another constraint of this A. Also, A also needs to get the data. Alright?
Okay.
Also, A also get data, alright? Not only E, okay? Alright? So, what's rank? In a matrix. So, this is a 3 by 3 dimension. Actually, because the data, if we treat each row as one entry of any training data, okay? some data are highly correlated, right? So if we do this the matrix calculation, some rows can be represented by other rows. Okay. So if we do this matrix, for example, in this matrix, so the first row times 2 plus second 2, okay, and then on we can have this matrix. This one is equivalent to this, right? So the right here actually 2 rows. Means we can only use these 2 rows. So this one is redundant, right? Can be represented by other rows. Okay. So back to the PCA or back to subspace. Actually, given data in 3-dimensional space, actually the data is only really explained in 2-dimensional space. So we can only discuss the problem in 2-dimensional space rather than original 3-dimensional space. So this is one. So all one rank corresponds to one component, one dimension. Okay. So that's why we keep it rank as low as possible, and we keep the dimension, the number of dimensions as low as possible. Why we need to use a low rank? Okay. So first, the data only covers a small part. And second, the intra-class. Okay. So within the class, some let's why they are in one class. Some class they are highly correlated, right? Some data can be represented by other class. Don't worry, okay. I have
There's an error on mine.
So this one, given this one, okay, we convert this one to a convex optimization, okay, using the Lagrangian application, okay. Okay, and there are actually 2 steps. One is you use SVD, signal modeling decomposition, iteratively, right? And one is the linearization. So in practice, this is what I did in the experiment. Because this one highly depends on the initialization of this multiplier. Okay, I use a dual approach to get an initial y first, right? And then can speed up the SVD procedure.
So what's line 14? Let me ask you that.
Wow. Another loop.
Another loop?
Another loop.
But what does it say?
K, actually K equals K plus.
So which node do you choose for A? Which node do you choose for A? So you have A, you have some star. So what the stars.
Right.
This star means a nuclear non.
Okay.
Nuclear non. Non, alright? Okay. The same A. This is matrix, okay? This is a nuclear non.
Do you want to unpack this for us, or do you just want to skip over it?
Huh?
Do you want to unpack this for us? I'm interested. Do you want to unpack it for us, or do you want to just move on? Do you want to unpack it for us? I'm interested in what you're doing. Yes?
You can ask me.
Okay,
Even
so you got D,
Yes.
right? And the question is to derive A and E from that. That's the goal.
So we only know D. Yes.
Yes, you know D, and you want to get a good A and a good E.
Yes.
So you start out with Y naught, which is what?
Why? Okay. Why is this multiplier? Okay. This is cause here there's no y, right? Because this one, the function, original function, if we want to minimize the function will be like this, right? So we use this one, we introduce y to convert this one to a convex problem, right? So this y, so also we update the y until, so by introducing y, in the end, we will get YAE. We start from 0, y, for example, initialize to 0, okay? Later on will be updated to something, okay? Alright?
Can you remove these 2 red circles so we can clear up?